Welcome to the next video, everybody. Today we're going to be talking about flatness, and we're going to be revisiting Raynaud's theorems from chapter 5 in a little more detail. So let's get into this. Recall that for a field f of characteristic 0, all finite f group schemes are tall over f. We talked about this in chapter 5. And so with a choice of algebraic closure f bar, there's an order-preserving equivalence of categories between finite flat group schemes over f and finite discrete modules over the absolute Galois group of f. Okay, so I think a lot of this is like talked about in detail in a lot of infinite Galois theory courses. I think Milne's notes talk about this. Okay, so let's define flatness more generally than I think we ever have before. Let K be a field of characteristic 0, which is the fraction field of Henselian, e.g. complete, for example, discrete valuation ring R with residual characteristic P. Fix an algebraic closure K bar. We'll say that a continuous representation ρ from the absolute Galois group of K to aught M on a finite abelian P group M is R flat, or just flat if R is understood, if there's a finite flat group scheme H over R, such that the GK representation given by the K bar points of H is isomorphic to ρ, or equivalently, such that the finite K group scheme canonically attached to ρ is the generic fiber of a finite flat group R scheme. So, familiar to what we were talking about back in chapter 1, but a little more general, although not actually quite as inclusive as we need it to be, as we'll talk about on the next slide. The flatness in the definition refers to the map H to spec R, by the way, in case you were wondering. Note that this kind of flatness is only really defined for finite Galois modules, but the definition can be extended to work for things like Tate modules of elliptic curves, which we will do in this chapter and which we have done before. Finally, note that the order of H is the size of M, it turns out, which is not hard to check. You can check it after passage to a geometric fiber where it's obvious. Geometric fiber over the generic point where it's obvious. Why are you allowed to do that? That's because of the R flatness. Okay, so let's motivate Raynaud's theorems a little bit here. If there were many choices for H given ρ, then this notion of flatness would not be very natural, right? If, in addition, ρ had extra structure, like that of a K vector space with a K action commuting with the GK action, then we would want such a structure to extend to H, or else this flatness concept just wouldn't really be useful. It would be too weak for us to use. So Raynaud's theorems address this concern. Okay, so let's talk about those. First, let's talk about Raynaud's equivalence of categories. Theorem 14.3.3, let R, K, and GK be as above, and consider the covariant functor f sub r from H to the K bar points of H, from the category of finite flat P power ordered R group schemes to the category of flat GK modules. When the ramification index E of R is less than P minus 1, so that P isn't 2 in particular, this functor is an equivalence of categories. Moreover, the category of finite flat P power order R group schemes is an abelian category with the usual scheme theoretic kernel and quotient, so you get to do all that kind of exact sequence stuff in that category. Okay, the only other, E of R can't be bigger than P minus 1, but it's either less than P minus 1 or it equals P minus 1. In the case E of R is P minus 1, and V is a continuous K-linear representation of GK on a one-dimensional vector space over a finite field K of characteristic P, if we assume that the FP bracket GK module underlying V is simple, meaning that the natural map FP bracket GK to K is surjective, then there is either a unique up to canonical isomorphism, finite flat R group scheme H, such that H of K bar is isomorphic to V, or there are two such R group schemes, one étale and the other multiplicative, meaning has a tall Cartier dual. So in this case here, we don't actually have an equivalence of categories, but we can still fully understand what happens, and there's really only two options. Okay. The last part of the theorem is, finally, the essential image of FR is stable under passage to subobjects, quotients, and finite direct sums with no restrictions on E of R. So this is in any case. We will need this. Okay. So proof, see chapter 5. We talked about the proof. You can see Raynaud's paper. You can see CSS, page 384. The proof is pretty well documented in several different places. I'll talk a little bit about the proof idea, though, because the proof idea will build us up to Raynaud's other theorem that we're going to need. Raynaud's proof builds up things from the case of finite flat R group schemes of with generic fiber representations that are simple of just P power order. So consider a finite discrete GK representation V with P power order. Consider one of these guys. How many, if any, finite flat R group schemes H admit V as a generic fiber representation, i.e., how many H are such that V is isomorphic to H of K bar as GK modules? Well, by Galois descent of schemes, you can see the Bosch neuron model book, chapter 6 for this. Knowledge of such an H satisfying this property is equivalent to the knowledge of V and of H cross RSH, where RSH is the strict Henselization of R. For example, when R equals ZP, RSH is this kind of unramified, we call it ZP un, it's like the maximal unramified extension of ZP. You can see BLR chapter 3 for this. So what this tells you is that, when you're arguing here, you can just replace R by RSH and GK by, the inertia group at K, which is just G of KSH, it turns out. Okay, so that makes things simpler to argue. Once we are in that setting where R is strictly Henselian and V is simple, we know that K equals N GKV. So this is the GK maps of V. This is a finite division ring. Well, then by Wedderburn's little theorem, it has to be a field of characteristic P. So V is canonically an irreducible K bracket GK module with finite K dimension. However, R is strictly Henselian and it's a DVR with residue characteristic P. So GK has a pro-P normal subgroup, which is wild inertia, and a pro-prime to P abelian quotient, which is tame inertia. You can conclude from this, and you can see, I don't know what SLF means here, Sayre local fields, chapter 9, that V is a tame, hence abelian representation. And so, from the structure theory of semi-simple rings, it turns out that dim KV is actually 1. It's not just finite, it's 1. Okay, well, what is V as a representation, a GK representation given by then? Just a continuous character psi from GK to K star. Raynaud's other theorem then successfully describes what these psis can actually be. Which psi can arise in this way? We're going to state his result over QP, as that is all we will need, and there's no need to muddle up the mixture here. We'll call this Raynaud's classification theorem. Again, we covered this back in chapter 5. We'll call it Theorem 14.3.4 here. It says, consider a continuous character psi from GQP un from IP, the inertia group at P, to K star, where K is a finite field of characteristic P. Choose an embedding of K into FP bar, and let V be a one-dimensional K vector space with IP action given by this psi here. Okay? Then V is ZP on flat, which is the case we care about. Remember, when we're working with QP on and ZP on. If and only if psi equals psi sub n to the E. What is this n? Well, the cardinality of K is P to the n. That's where the n comes from. What is psi sub n? It's the fundamental character of level n. I think we talked about this at the beginning of the chapter. Okay? And then what is E allowed to be? It has to be of the form E naught plus E1P plus dot 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 plus En minus 1 P to the n minus 1, where these EIs are between 0 and the ramification of index of ZP un, which is just 1. Okay, so the EIs have to be between 0 and 1. Okay, so for a proof of this, again, you can see chapter 5 or wherever you like. The conclusion is as follows. For a continuous unramified character chi from GP to FP cross, so remember, unramified means when we strict to inertia, we're trivial. The cyclotomic character to the ith power times chi from GP to FP cross is flat if and only if I equals 0 or 1 mod P minus 1. That's the only time we can actually satisfy this condition here, because remember, n equals 1 in this case, right? So basically, the cyclotomic character is the first fundamental character. And so n up here is 1, and this condition here really reduces to just, I'll let you check this, I equals 0 or 1 mod P minus 1. That's an easy exercise. I just did it last night, actually, in preparation for this. So, what's the upshot here? What am I getting at? I mean, look, there's just not very many options. There's not very many options for a character like this to be flat. We're really restricted here. Flatness is quite a severe condition to put on a representation. That's kind of what I want you to get out of this. Okay, so we will finish. There's a gap in the proof of our first theorem of the chapter that we are now able to fill in using Raynaud's theorems. It's the irreducible case when we were looking at GP representations attached to elliptic curves. We didn't prove the irreducible case, so we will do that next time using these theorems. So thanks for watching, and I'll see you then.